Hello there, my friends. Welcome to Lab 6, which is the last lab for this semester. For today's lab, we will see active filters, which are low pass, high pass, band pass, and band stop filter. Band stop filter is also known as band reject filter or notch filter. For active low pass filter, we expect this filter to eliminate the high frequencies and let the low frequencies pass. We know that the reactance of any capacitor is inversely proportional to the frequency. So, here is our capacitor and it will stop DC and it will let the AC to pass. So remember this figure. So it will simply let the higher frequencies flow through this line. So the lower frequencies will remain. For a DC voltage, so as we know that the frequency of any DC voltage is 0, this capacitor will act as an open circuit. We will assume that there is no capacitor for DC voltage. Now we have a simple non-inverting amplifier circuit, and here is the gain of it. Now, for our filter design, we need a cutoff frequency. As we know, if you plot the body diagram, if you assume that here's the maximum gain point in dBs, here is our cutoff frequency, minus 3 dB below the maximum gain. This is the cutoff frequency. For low frequencies, we expect The passband gain of the filter, which should be the maximum gain, should be okay. For the frequencies lower than the cutoff frequency, the gain should be equal to the passband gain, which is equal to the DC gain of the op-amp for low pass filter. For the cutoff frequency gain, we will multiply the passband gain by 0.707. For the frequencies bigger than the cutoff frequency, we expect the smaller gain. We expect a gain smaller than the passband gain. Now, we have a Proteus circuit for each filters. Here's our low pass filter, and here is our body diagram. Now just take an op-amp from the library For this experiment, let us use LM741. If you take the ideal op-amp, we will see ideal characteristics. However, in order to see the real-life characteristics of any op-amp, don't take this ideal op-amp. Instead, pick LM741. Supply voltage for the negative side is minus 15 volts. And for the positive one, 15 volts. Here are our resistors and a capacitor. You can pick any capacitor you want. For this experiment, you can pick cap or capacitor device. It's not important. We have capacitor. And take a generator as sine, because we will test our circuits using the sine wave. The frequency at this moment and the amplitude is not important because we will plot the gain versus frequency graph, which is our body plot. You should take a voltage probe at the output side And we are ready to draw our body plot. How? Let us do it again. You should enter in the graph mode, frequency or AC sweep graph we need. Maybe the frequency is way better. Let us draw it. And here it is blank. What is the name? Low pass filter. And what is the reference? The reference is our input. What is it? R3 bracket 1. Let's find it. RT bracket 1. Start frequency and stop frequency. What are these? It means that we will start our experiments with that frequency and stop our experiment with that frequency. The program Proteus will start to change the frequency of that generator with respect to these parameters. So let's start from 1 and end at 1 megahertz. Click OK. It's again a blank graph. We forgot to add an output. Right click on it, add traces, and prop P1. What is it? U1 bracket OP. U1 bracket OP. Okay. Now it is blank again. Now right click on it, then simulate graph. And here is the body plot of our circuit. What does this body plot say? Right click, maximize. Now here's our cursor. Here we can see the frequency and the gain. The gain is 12 dBs. Now we are searching for 3 dBs below the passband. Which corresponds to 9 dBs. Here is the cutoff frequency, approximately 3.41 kilohertz. In order to make sure that the body plot is correct, let us, and this is 39 kilohertz, which is approximately 3.41 kilohertz. Okay, now what about the voltage gain in terms of passband gain of the filter? AF is equal to 1 plus R2 over R1. R2 and R1 corresponds to R4 and R5 in the circuit constructed in Proteus, which corresponds to 300K over 100K. AF is equal to 1.300K over 100K. AF is equal to 4. Now AV is equal to 4 over square root of 1 plus square of F over FC was equal to 3.41 kilohertz. Let's put square. Maybe we should put the theoretical values to the denominator parts, which was 3.39 kilohertz. If you take F as cutoff frequency, AV will be 4 over square root of 2, and it will be 4 times 0.707. Now, for our high-pass filter, we will do the same operations actually. What is the DC gain? -4. Sorry. 4, because it's non-inverting amplifier. The cutoff frequency is the same as before, which was 3.39 kilohertz. Now the voltage gain will be 4 times F over 3.39 kilohertz over square root of 1 plus F over 3.39 kilohertz square. So let's talk about the high pass filter at this time. Now the high frequency signals can easily pass through this capacitor, and low frequency signals cannot pass through this capacitor, and this will simply amplify the high frequency signals. So what about the active bandpass filter? By the way, we totally forgot to mention about the body plot of high pass filter. Here the maximum gain is approximately 12 decibels, and 3 dB below of it is approximately here. As you can see, 3.39 kilohertz. This event is not the desired one, because for this region we are at the limit of op-amp's frequency response characteristics. For very high frequencies, the op-amp will act as a low pass filter. So this region is not desired one. For LM741 op-amp, Proteus says that if you apply more than 50 kilohertz, the gain will dramatically decrease. So about the bandpass filter, again, we want op-amp to pass a certain frequency to its output. So for this circuit, here are our resistors and capacitors. Let us put the numbers into the formula. Fr is equal to 1 over 2 pi times square root of 10 times 22, 10 times 22 times 10 to 6 times 10 times 10 times 10 to minus 9, minus 18, we have 1073 Hertz. This is our resonant frequency for bandpass filters. So we expect that for this frequency, this filter will give the maximum gain. We expect it to select that frequency. Now let's see. Here's the maximum gain. And here's the frequency. It is approximately equal to the result of the formula. This Q stands for the quality factor of the bandpass filter. Smaller the bandwidth will make the quality bigger. Let us determine the lower cutoff frequency from the body plot. The gain is 0.702 dBs. Note that this is millidBs. 3 dB below this number corresponds to minus 2.3 approximately. Okay, here's our lower cutoff frequency. By the way, do not forget, these values are not precise. We are just making lots of errors during the reading process of these numbers from the plot. Okay, let us say that the lower cutoff frequency is 566 hertz. 566 hertz. And what about the higher cutoff frequency? It is 2.05 kilohertz. The bandwidth is equal to F high minus F low. It is approximately equal to 1484 hertz. Now let us calculate FR again. F low times F high. It is approximately equal to 1077 hertz. And what about the quality? Equal to 0.77 over 1484 which is equal to 0.73. They are all, by the way, approximately equal. Now it should be equal to 1 or 2 square root of what is R2? (22 kilo ohms over 10 kilo ohms). Which is approximately equal to 0.74. So what about the maximum gain? Maximum gain should be minus R2 over 2R1 should be equal to 2Q to 2, which was that equation, by the way, equal to minus 1.1 should be equal to minus 1, 0, 1. If we take Q as that value. Okay, what about the active bandstop filter? This is nothing more than the summation of the low pass filter and the high pass filter. We will just add two different filters separately and we will get this output. Here's the example. Here's the result. It will just cut off a certain frequency. It will reject a certain frequency, which is 100 Hertz. Let us put two different graphs. This graph is for low pass side. This graph is for high pass side. U4 OP and U5 OP. Simulate graph and simulate graph. The addition of these two graphs will give that graph. This is a summing amplifier, by the way, and the gain of this summing amplifier is -1. Let us memorize the formula. This input times this resistor over this resistor, and this input times this resistor over this resistor. Okay, I think there's no need to calculate the active band stop filter parameters, because it is nothing more than the combination of two different filters. And I think that's all for this term. Thanks for watching, guys. For any questions, please send email to Barış Yılmaz or me. And good luck with your final exams. See you later.